Look up at the night sky, you see stars. Maybe you see a planet like Mars or Jupiter. They shine brightly. But what about Uranus? It is out there. It is the seventh planet from our sun. It is very, very far away. You usually need a telescope to see it. Even then, it looks like a small, faint bluish-green dot. It is a quiet, distant neighbor in our vast solar system. For a long time, Uranus did not seem to do much. It just spun on its side, a tilted giant. Uranus was the first planet discovered using a telescope. William Herschel found it in 1781. He first thought it was a comet, or maybe a star. But it moved differently. It followed an orbit. Scientists realized it was a planet, a very big one. It is about 4 times wider than Earth. Imagine that. 4 Earths could fit side by side across Uranus. It is an ice giant. This means it is made of icy materials. These are not just water ice. They include methane and ammonia ices too. For many years, Uranus was a bit of a mystery. It is so far from Earth. It is hard to study in detail. Our early telescopes showed us a mostly featureless blue-green sphere. It seemed calm. Almost boring, some might say. But the universe is rarely boring. It just waits for us to look closer. It holds secrets. And now, Uranus is starting to reveal some of its secrets. It is showing us that it is more dynamic than we thought. It is changing. These recent changes are exciting for astronomers. The planet appears to be getting brighter. Its physical structure, especially its atmosphere, seems to be shifting. Why is this happening? What does it mean? These are the questions scientists are asking. We are using powerful new telescopes. We are looking at Uranus with new eyes. We are trying to understand this distant world. This is what science is all about, exploring the unknown. And Uranus, our faint blue dot, has become a hot topic of cosmic investigation. So, what is Uranus made of? It is not like Earth. Earth is rocky. Uranus is an ice giant. This name can be a little tricky. The ices inside Uranus are not like ice cubes in your drink. They are super hot. They are also super dense. This is because of the immense pressure deep inside the planet. Think of it as a slushy mix of water, methane, and ammonia. This mixture surrounds a small, rocky core. This core is probably about the size of Earth, but it is buried under layers of these exotic ices. Above this icy mantle is Uranus's atmosphere. This atmosphere is very thick. It is mostly hydrogen and helium. These are the lightest gases in the universe, but there is also methane in its atmosphere. This methane gas is important. It is what gives Uranus its blue-green color. Methane absorbs red light from the sun. It reflects blue and green light back into space. So when we look at Uranus, we see these cool icy colors. It is like a giant cosmic aquamarine gem, far out in the cold. One of the strangest things about Uranus is its tilt. It is tilted on its side by about 98 degrees. Imagine Earth tilted so much. The North Pole would point almost directly at the sun sometimes. This extreme tilt means Uranus has very extreme seasons. Each season lasts for about 21 Earth years. For decades, one pole faces the sun. Then, for decades, the other pole does. This must create some very unusual weather patterns. Scientists are still trying to fully understand how this affects the planet's atmosphere. The temperature on Uranus is incredibly cold. At the cloud tops, it can be around minus 214 degrees Celsius. That is minus 353 degrees Fahrenheit. It is one of the coldest planets in our solar system. Even though it is big, it does not generate much internal heat. Or, if it does, we have not detected much of it yet. This is different from Jupiter and Saturn. Those gas giants radiate more heat than they receive from the sun. Uranus is more of a cold, quiet giant. Or so we thought. For a long time, Uranus seemed like a very stable planet. When Voyager 2 flew by in 1986, it sent back images. These images showed a mostly bland, featureless world. There were some faint clouds, but nothing like the giant storms on Jupiter, or the beautiful rings of Saturn. Uranus appeared quite serene. Its atmosphere looked calm. It seemed like not much happened there. This view persisted for many years. It was the image we had of this distant ice giant. However, things have started to change, or perhaps our ability to see the changes has improved. With more powerful telescopes on Earth, like the Keck Observatory, and with space telescopes like Hubble, we can now see Uranus in much greater detail, and what we are seeing is surprising. The planet is not as placid as we once believed. There is activity, there are storms, there are bright spots appearing and disappearing in its atmosphere. This is a different Uranus. Scientists have noticed an increase in storm activity. Bright, cloud-like features are becoming more common. These are probably made of methane ice crystals. They form high in Uranus's atmosphere. Some of these storms are huge. They can be as big as continents on Earth. This shows that Uranus has a dynamic weather system. It is capable of producing powerful atmospheric disturbances. This is a big shift from the calm image Voyager 2 gave us. The sleeping giant seems to be waking up. These changes are not just about storms. The overall appearance of Uranus seems to be evolving. Some observations suggest changes in its haze layers. These layers can affect how bright the planet looks. They can also change its color slightly. The distinct bands in its atmosphere, similar to Jupiter's but much fainter, might also be changing. It is as if the planet's atmospheric circulation is undergoing a significant shift. We are witnessing a transformation, a slow, grand transformation on a planetary scale. So why is Uranus's physical structure, especially its atmosphere, appearing to change? One major factor is its extreme axial tilt and its very long orbit around the Sun. Uranus takes 84 Earth years to go around the Sun once. This means its seasons are incredibly long. Each pole experiences 42 years of continuous sunlight, then 42 years of continuous darkness. We are currently in a period where the planet is approaching its solstice. This happened around 2007 for its northern spring or southern autumn. Now, in 2025, we are past that point. This slow change in solar illumination is likely driving the atmospheric changes. As different parts of the planet receive more sunlight, the atmosphere warms up. This can trigger convection. Hotter gas rises, cooler gas sinks. This movement can create storms. It can also change cloud patterns. We might be seeing a seasonal response. A very, very slow seasonal response. Like watching spring arrive on a planet where spring lasts for decades. It is a grand atmospheric adjustment. Another possibility involves changes deep within the planet. Uranus does not seem to have a large internal heat source like Jupiter or Saturn. However, even a small amount of internal heat could play a role. If this internal heat flow changes, it could affect atmospheric circulation. It could stir things up from below. Scientists are still debating how much internal heat Uranus has and how it might be escaping. This is a key piece of the puzzle. The composition of Uranus's atmosphere is also crucial. The methane clouds we see are just the tip of the iceberg, or rather the tip of the ice giant's atmosphere. There could be other types of clouds deeper down, clouds made of hydrogen sulfide perhaps, or ammonia. Changes in these deeper cloud layers could affect what we see at the top. It is like a complex weather system with many layers, and all these layers interact. We are just beginning to understand this complex atmospheric dance on Uranus. Section 5. Turning up the lights, Uranus gets brighter. One of the most intriguing recent observations about Uranus is its increased brightness. The planet seems to be shining more intensely than it did a few decades ago. This is not just a small change, it is noticeable. Astronomers measure planetary brightness carefully. They use standardized methods. The data suggests a clear trend. Uranus is reflecting more sunlight back towards Earth. But why would a planet suddenly get brighter? This is a fascinating question for planetary scientists. Several factors could be contributing to this brightening. One idea is related to changes in its cloud cover. If there are more bright clouds, the planet will reflect more sunlight. We have seen an increase in storm activity. These storms often produce bright, high-altitude clouds made of methane ice. If these storms become more frequent or larger, they could significantly increase Uranus's overall reflectivity. It is like adding more mirrors to the planet's surface, or, in this case, its atmosphere. Another factor could be changes in the planet's haze layers. Uranus has layers of photochemical haze in its upper atmosphere. This haze is formed when sunlight breaks down methane molecules. The properties of this haze can change. It can become thinner or thicker. It can also change its particle size. If the haze becomes less absorbing or more reflective, it could make the planet appear brighter. The exact nature of this haze and how it varies is still an active area of research. The viewing angle also plays a role. Because of Uranus's extreme tilt, we see different parts of the planet at different times. As it orbits the Sun, our perspective changes. We might be seeing a pole that is inherently brighter than its equatorial regions. Or perhaps the way sunlight scatters off its atmosphere changes with the viewing geometry. Scientists are carefully modeling these effects. They want to separate geometric effects from real physical changes on the planet. This is crucial for understanding the true nature of the brightening. Section 6. The science of the shine. What causes the glow? Let's dive a little deeper into the science behind this mysterious glow. The term glow might be a bit misleading. Uranus is not generating its own light like a star. It is shining because it reflects sunlight. So when we say it glows more, we mean its albedo has increased. Albedo is a measure of how much light an object reflects. A perfect mirror would have an albedo of 1. A perfectly black object would have an albedo of 0. Uranus's albedo seems to be on the rise. The increased storm activity is a strong candidate for this enhanced reflectivity. These storms dredge up material from deeper in the atmosphere. This material then freezes out at higher, colder altitudes. This forms bright white clouds of methane ice crystals. These crystals are very good at reflecting sunlight. So, more storms mean more bright methane clouds. And more bright methane clouds mean a brighter planet. It is a direct cause and effect relationship. Simple, yet powerful, on a planetary scale. Changes in the stratospheric haze are also very important. This haze is made of complex hydrocarbons. Think of it as a kind of smog. It forms high above the main cloud decks. This haze can absorb some sunlight. If this haze thins out, more sunlight can reach the reflective cloud layers below, and more reflected light can escape back into space. So, a thinning of this upper haze could make the planet appear brighter. It is like cleaning a dirty window to let more light through. Solar activity itself might also play a small, indirect role. The sun goes through cycles of activity, more solar flares, more energetic particles. These can affect the chemistry of a planet's upper atmosphere. They could influence how the haze particles form and behave. While Uranus is very far from the sun, it is not completely isolated from its influence. Understanding this connection between solar activity and Uranus's atmospheric optics is another piece of this cosmic puzzle. We are looking for all connections. Section 7. Distant cousins. Does Uranus's mood affect Earth? Now you might be wondering, do these changes on far-off Uranus affect us here on Earth? Directly? Probably not. Uranus is over 2.8 billion kilometers away. That is nearly 1.7 billion miles. Its gravity does not tug on Earth in any significant way. Its weather systems are self-contained. So a new storm on Uranus will not cause a hurricane on Earth. Our planets are too distant. They live their own separate lives in the vastness of space. However, studying Uranus and its changes is incredibly valuable for us. It helps us understand planetary science in general. Uranus is an ice giant. Neptune is its cousin. We do not have any ice giants in our inner solar system. By studying Uranus, we learn about how these types of planets form. We learn about their atmospheres. We learn about their climates. This knowledge helps us understand the diversity of planets in our own solar system, and in other solar systems too. Think of it as comparative planetology. We study Earth, we study Mars, we study Venus, and we study Uranus. Each planet is a natural laboratory. Each one shows us different physical processes at work. By comparing them, we can build better models of how planets work. This includes understanding Earth's climate. For example, learning about atmospheric dynamics on Uranus, even with its strange tilt and cold temperatures, can refine our models of atmospheric physics. These models are then used to understand our own world. Furthermore, understanding how the outer planets respond to solar variations gives us clues about the sun's influence across the entire solar system. The sun is our star. Its behavior affects all planets. By seeing how distant Uranus reacts to long-term solar cycles or changes in solar wind, we get a more complete picture of our solar system's environment. This broader understanding helps us appreciate the interconnectedness of our cosmic neighborhood, even if the connection is through shared physics, not direct impact. Section 8. Cosmic Clues. Why Uranus's changes fascinate scientists. These changes on Uranus are more than just a curiosity. They are important clues. Clues about how planets like Uranus work. Ice giants are common in the galaxy. Many exoplanets we are discovering around other stars are similar in size and mass to Uranus and Neptune. But we know so little about them. Uranus is our local laboratory. It is our chance to study an ice giant up close, or as close as we can get from billions of kilometers away. The increasing storm activity and brightness challenge our old models of Uranus. For a long time, we thought its atmosphere was relatively stagnant, especially compared to Jupiter or Saturn. The new data forces us to rethink. We need new models. Models that can explain these dynamic weather patterns. Models that can account for the brightening. This is how science progresses. Observations lead to questions. Questions lead to new theories. And new theories lead to new understanding. Understanding the energy balance of Uranus is a key goal. How much energy does it get from the sun? How much internal heat does it generate, if any? And how is this energy transported and released through its atmosphere? The current changes could be linked to a subtle shift in this energy balance, perhaps due to its long seasonal cycle, or perhaps due to processes happening deep inside. Answering these questions will tell us a lot about the evolution of giant planets. These observations also highlight the importance of long-term monitoring. Planetary changes can happen slowly, very slowly, on human timescales. Uranus's year is 84 Earth years long. To understand its seasons, we need to watch it for decades, even centuries. The recent changes we are seeing now might be part of a much larger, longer cycle. This is why continuous observation with powerful telescopes is so vital. It allows us to piece together the long story of these distant worlds. Each new image, each new data point adds a word to that story. Section 9. The quest continues, peering deeper into the blue. So, what is next for Uranus? How can we learn more about its mysterious glow and changing face? The scientific community is buzzing with ideas. We need more observations, consistent high-resolution observations, using our best ground-based telescopes, like those on Mauna Kea in Hawaii, or the Very Large Telescope in Chile, and of course, space telescopes like Hubble, and its successor, the James Webb Space Telescope, or JWST. JWST can see in infrared light. This is perfect for studying Uranus's cold atmosphere and its heat. Scientists are also dreaming of a new space mission to Uranus. Voyager 2 gave us a quick glimpse in 1986, but that was just a flyby. We need an orbiter, a spacecraft that would go to Uranus and stay there. It would circle the planet for years. It would map its atmosphere in detail. It would measure its magnetic field. It would study its rings and moons. Such a mission is a high priority for planetary scientists. It would revolutionize our understanding of ice giants. This future mission could carry advanced instruments, cameras that see in different wavelengths, spectrometers to analyze the composition of the atmosphere, magnetometers to study its strange magnetic field. It could even drop a probe into Uranus's atmosphere. Imagine that, a probe descending through those methane clouds, measuring temperature, pressure, and wind speeds, sending data back to Earth. That would be an incredible journey of discovery. It would answer so many of our current questions. In the meantime, researchers will continue to analyze existing data. They will build more sophisticated computer models. These models will try to simulate Uranus's atmosphere. They will try to reproduce the observed changes. This combination of observation and theory is powerful. It is how we unlock the secrets of the universe. Uranus, the once quiet giant, is now showing us its dynamic side. It is inviting us to look closer, to learn more. And the quest to understand this distant, glowing world is just beginning. The cosmos awaits.